Hello students, this is our fourth lecture of chapter first, complex number from part 2. In today's lecture, we will study about Argand diagram. It is also called as complex plane. Modulus of Z means modulus of complex number. Argument of Z in different quadrants or axes. Properties of modulus of complex numbers and properties of arguments. Polar form of complex number and exponential form of a complex number. So first we discuss about Argand diagram or the complex plane. Now we know in the xy plane we represent the points. Similarly, any complex number can be represented in coordinate system using some point, and such a diagram is called as Argand diagram. So first we see a complex number z is equal to x plus iy. A complex number z is equal to x plus iy where x and y are real numbers and I is equal to square root of minus 1 is expressed as the point in the plane whose coordinates are ordered pair xy. Means in the here we represent this complex number x plus iy by using the coordinate having the ordered pair as xy. Means the x coordinate is represented by its real part and y coordinate of the point is represented by the imaginary part. Now let z is equal to x plus iy be a complex number, then the point Pxy represents the complex number. Now see the diagram. Here this Pxy represents the complex number z. Okay. Now here from the figure we observe that x is the real part of z and y is the imaginary part of z. Means x is related to the real part and so it is the distance of the point from the y-axis and y is the distance of the point from the x-axis. X is the real part of z and it is represented on the x-axis. So this x-axis is called as real axis. Similarly, y is the imaginary part of z and it is represented on y-axis. So y-axis is called as the imaginary axis. So here x is equal to real part of z is represented on the x-axis. So x-axis is called as real axis. Similarly, y is equal to imaginary part of z and is represented on y-axis. So the y-axis is called as the imaginary axis. Okay. Now here from this figure we observe that a diagram which represents the complex number by the point in a plane with reference to the real and imaginary axis is called as the Argand diagram. This is the proper definition for the Argand diagram. And so a diagram which represents complex numbers by points in a plane with reference to the real and imaginary axis is called Argand diagram or the complex plane. This is about Argand diagram. Now the next part is modulus of z, means modulus of complex number. So if z is equal to a plus ib is a complex number, then the modulus of z is denoted as in this way and it is called as mod z. or simply we represent it by r, is denoted as mod z is equal to square root of a square plus b square, or r is equal to square root of a square plus b square. Now again this complex number can be represented in the Argand diagram by using a point having coordinates are AB. And so let PAB represent the complex number z is equal to a plus IB, and therefore r is equal to mod z, which is equal to square root of a square plus b square, and it is nothing but the distance of point P from the origin, that is OP. If we see here the figure, we observe the figure in this way here. So obviously the distance OP is the mod z, means the distance of the point P from the origin is called as the modulus of complex number, and it is denoted by r. So again, as the coordinates of point P as AB, and so distance OM is A and distance PM is B here. Now hence modulus of complex number is the distance of point P from the origin, where point P represents the complex number Z in the plane. Okay. Now see the argument of Z. OP makes an angle. This OP makes an angle with the positive direction of x-axis, and that angle is called as the argument or amplitude of complex number. And so here theta is called the argument or amplitude of complex number Z is equal to a plus IB, and it is denoted by ARG of Z. We read it as argument of Z. Okay, means the modulus is the distance of the point which represents the complex number from the origin is the modulus of the complex number, and the argument is the angle made by OP with the positive direction of x-axis. This is called as the argument of Z. And so from this figure now we can find the value of sin theta and cos theta. From the figure, sin theta is what? PM divided by OP, that is B upon R. And cos theta is OM divided by OP, that is A upon R, where R is the distance, so it is not equal to 0. And therefore, from the figure now we get, I recall this figure again here. Okay, we don't draw this again. For the explanation, I draw this figure again on the next page here. So from this figure, now we write the values of sin theta and cos theta. Therefore, sin theta is B upon R and cos theta is A upon R, where R is not equal to 0. So B is equal to R sin theta and A is equal to R cos theta. And therefore, from this we can find the value of tan theta. It is B upon A, if A is not equal to 0. And therefore from this theta is equal to tan inverse of B upon A, and it is theta is nothing but the argument of complex number, means argument of Z. Now see the next topic, argument of Z in different quadrants or axes. So for that we see one table. Now here for a complex number Z is equal to A plus IB, we consider different cases for values of A and B. And for that different values of A and B, we see the quadrant or the axis, and theta means the argument Z. So the first case is A greater than 0, B is equal to 0. That means when A is positive and B is 0. The axis is on positive real axis and theta is 0, means here argument is 0. When A is greater than 0 and B is greater than 0, at that time it is in first quadrant and argument Z is theta is equal to tan inverse 1, that means pi by 4. Now, when when A is equal to 0 and B is greater than 0. At that time here, axis is on positive imaginary y-axis and theta is equal to pi by 2. When A is less than 0 and B is greater than 0, it is in second quadrant and argument z is equal to means theta is equal to tan inverse of B upon A plus pi, where theta is lies in pi by 2 to pi because it is in second quadrant. When A is less than 0, B is equal to 0. The axis is on negative real x-axis and theta is equal to pi. When A is less than 0 and B is less than 0, that means when both are negative, then it is lies in the third quadrant and theta is equal to tan inverse B upon A plus pi. And since theta is in third quadrant, means theta lies in pi to 3 pi by 2. When A is equal to 0, B is less than 0. On its axis is on negative imaginary y-axis. And so theta is equal to 3 pi by 2. When A is greater than 0, B is less than 0. It is in fourth quadrant and therefore theta is equal to tan inverse of B upon A plus 2 pi. Where theta is in fourth quadrant, that means theta lies in between 3 pi by 2 to 2 pi. Now students, make here one correction. Here theta is equal to tan inverse of B upon A. Instead of this pi by 4, we write here theta as here in this second term here theta is equal to tan inverse of B upon A. Make here the correction. Remember this. Okay. So these are the different values for the axis or quadrant and argument z. Now we see the next topic, properties of modulus of complex number. So the first we see, if z1, z2, z3 are the complex numbers, then the first property is that mod z is equal to 0 if and only if z is equal to 0. That means the modulus value of complex number is 0 if and only if the complex number is 0. That means in that real part and imaginary part both are 0. Second one is mod z is equal to mod minus z is equal to modulus value of z bar is equal to modulus value of minus z bar. That is, the modulus value of all the for all these complex numbers are same. That is mod z, modulus value of negative of z, modulus value of conjugate of z, and modulus value of negative of conjugate of z. All these values are same. Third, minus mod z is less than or equal to real part of z, which is less than or equal to mod z, and minus mod z is less than or equal to imaginary part of z, which is less than or equal to mod z. 4. Z into z bar is equal to mod z square. 5. Mod z into z2 is equal to mod z1 into mod z2. Means the modulus value of product of two complex numbers is same as product of their modulus. 6. Mod z1 upon z2 is equal to mod z1 upon mod z2, where z2 is not equal to 0, means the complex number in denominator is non-zero. That is, the modulus value of ratio of two complex numbers is same as ratio of their modulus. Property number 7, mod z1 plus z2 is less than or equal to mod z1 plus mod z2. That is, modulus value of sum of two complex numbers is less than or equal to sum of their modulus. 8. mod z1 plus z2 square is equal to mod z1 square plus mod z2 square plus 2 times real part of z1 into z2 bar. 9. Mod z1 minus z2 square is equal to mod z1 square plus mod z2 square minus 2 times real part of z1 into z2 bar. Property number 10. Mod z1 plus z2 square plus mod z1 minus z2 square is equal to 2 times mod z1 square plus mod z2 square. 11. Property number 11. Mod a z1 minus b z2 square plus mod a z1 plus b z2 square is equal to a square plus b square into mod z1 square plus mod z2 square, where a comma b belongs to real number. Now see properties of arguments. If z1, z2, z3 are the complex numbers, then first property, argument of z1 into z2 is equal to argument of z1 plus argument of z2. Second, argument of z1 upon z2 is equal to argument of z1 minus argument of z2. Third, argument z plus argument z bar is equal to 0 and argument of z into z bar is equal to 0. Argument of z bar is equal to minus argument of z, which is equal to argument of 1 upon z. 5. If argument of z is equal to 0, then z is real. Means when the argument of a complex number is 0, then the complex number is only a real number, or it is purely real. Next topic is polar form of complex number. Let z is equal to a plus ib be the complex number represented by the point P of AB. See as shown in figure, here P of AB, it is the complex number which is shown in this Argand diagram. Now here the measure of angle XOP, it is theta, and which is argument of Z, so it is tan inverse of B upon A. And OP is the distance of point P from the origin, therefore OP is equal to modulus Z means R. It is equal to square root of A square plus B square, and which is greater than 0. Then P of R theta is called the polar form of point P. Now we call the origin as pole. Here this origin is called as pole. As A is equal to R cos theta and B is equal to R sin theta, we get Z is equal to A plus IB becomes now Z is equal to R cos theta plus R sin theta into I. Make here one correction. Here is I there. Make this correction. R cos theta plus R sin theta into I. And if we take here R as the common part, inside the bracket we remains with cos theta plus I sin theta. And therefore Z is equal to R into cos theta plus I sin theta. This is called the polar form of complex number A plus IB. Now see the next part, exponential form. It is known and can be proved using special series that e raised to I theta is equal to cos theta plus I sin theta. And therefore Z is equal to A plus IB, which is can be written as R is equal to R into cos theta plus I sin theta, and it is equal to R e raised to I theta, where R is equal to mod Z and theta is equal to argument of Z, is called as an exponential form of complex number. So this is about today's lecture. So see you again in the next lecture. Thank you.